Okay, so now we're going to look at what's often called the most important concept in category theory. And this is universal properties, okay, universal morphisms. We're basically going to understand what the kind of categorical version of perfection is in some sense, okay? Recall when we did the construction of products, we used this kind of idea that we can, find the best candidate for the job. And now we're going to see this idea in full generality. And it's so important. Like, there's so many different things. We're going to be able to define what natural numbers are, okay? So, this infinite set of natural numbers, 0, 1, 2, 3, and so on. We're going to be able to define what that is in categorical terms. We're going to be able to define what the set of functions is from A to B in categorical terms. And we're going to see how those properties correspond to universal morphisms, universal properties, okay? We're also going to see how the categorical product corresponds to one of these things. I mean, there's so many constructions in category theory which are kind of ways to recognize a substructure in a category which have meaning, okay? So if I see this substructure, it means such and such. And so I'll look for it in other categories and so on. And like so much of the time, this corresponds to a so-called universal morphism. Universal morphisms are basically, they really almost give us a definition of what perfection means in category theory, because it's this kind of universal template, this kind of template that we can keep using to keep finding the kind of best objects for the job in different contexts. And it gives us so many different things. So, I mean, we're going to do so much today. We're going to see how the kind of set of arrows from one category into another can be represented by an object itself. So there's a kind of self-referential nature to some categories. Like, there's a set of functions from A to B, which is like an object in the category set that represents the collection of all arrows from A to B. It's kind of curious. We're going to look at this definition of this natural number object, which I am still sort of, I just think it's amazing that we can define this kind of infinite sets in terms of a little diagram in category theory. We're going to see how that corresponds to a universal morphism. We're going to define what universal morphisms are. We're going to show that any two universal morphisms similarly defined are isomorphic to each other. We're going to get so much out of this. All we have to do is understand the definition of a universal morphism, and then we're just going to see it apply like everywhere. But now I'm going to define the idea of an initial morphism. And basically, this is the core content of the idea of universal properties. There's a few pieces of terminology, but I'll explain that as I go along. Basically, the idea is that we have some category C and we have some category D. And there can be something which is called an initial morphism. And we say it's an initial morphism from an object X, in this category D, to a functor V. A functor from this category C into this category D. So that's a bit strange, isn't it? We're saying something that's from an object to a functor. I mean, normally objects and functors live kind of on different levels. There is a way in which this makes sense, but just accept it at the moment as terminology, okay? So, okay, what is this thing then? What is the initial morphism? Well, it's actually two things. It's a object, P, in this kind of source category C here, and it's an arrow, so it's an object P paired with an arrow phi in this target category, and that goes from X into V of P. And it has to be such that the following property is satisfied, this property written in red, this property called the initial property. What is the initial property? It basically says that for any other thing like this, its effects can be kind of replicated by a unique intermediary arrow. It's the same kind of deal that we saw with products earlier on. So basically what we're saying is that for every object y in C and every arrow k in D, which goes from x to v of y, there's going to exist a unique arrow from P into Y, which has the property that it makes this diagram commute. So K is equal to V of I after phi, okay? K is equal to V of I after phi. And that's it, okay? So we just defined initial morphisms and initial properties. Now let's define the dual. So we're going to define terminal morphisms and terminal properties. Now look at the diagram here. It's just the same as the diagram I last showed you, except I've reversed all the arrows within the categories. And that's basically all we have to do for this definition. So the definition of a terminal morphism, now we say it's from the functor v to the object x. So we have this functor here from C to D, okay? And it goes, we're saying it goes from V to X. Well, what is it? Well, it's an object P in this source category C and an arrow phi, which goes from V of P into X, okay? And it has to be such that this terminal property is satisfied. What's the terminal property? It says that for any object y in this source category and any arrow k, which goes from v of y into x, there's going to be this unique intermediary arrow from y into p, such that its image, v of I, makes this diagram commute, okay? So for every y in C and every k from v of y into x, there exists a unique I from y to p, such that k is equal to phi after v of I, okay? So this is the definition of a terminal morphism. So now we can finally define what a universal property is, okay? We've seen the terminal property and we're seeing the initial property. So would say a universal property is something that's either an initial property or a terminal property. And here's the definition of a universal morphism. That's just something that's either an initial morphism or a terminal morphism. So now we have this terminology and we know one of the most important definitions in category theory, this idea of a universal property. I mean, these occur all over the place in so many constructions. And one of the nice things about this is that, as I'll demonstrate later, any two universal morphisms, let's say initial morphisms, okay, from a particular object to a particular functor, are going to be isomorphic to each other. So this kind of isomorphism feature, which we keep using again and again, is actually possessed by these universal things. And this is going to save us a lot of work, okay, because we won't have to keep cooking up specific sort of universal constructions of different things and then keeping arguing why they're isomorphic. We can show that it holds in general for any universal morphism. Okay, so now we know about universal properties. Let's see some examples, because there are just so many examples. I mean, most of the interesting kind of gadgetry that people look at in category theory corresponds to these kind of universal morphisms. And one very sort of main example is this categorical product, which we've already seen. So what we're going to do now is we're going to define a couple of categories, and a special kind of functor, and then we're basically going to say, okay, what's going to be a terminal morphism related to this construction? And that's going to turn out to be precisely the categorical product of a couple of objects. So here's the setup then. We have a general category C, and within this category we seek to find the categorical product of a couple of objects, X and Y, okay? And so what we're going to do is we're going to take this category C and we're going to make a new category which is the product of this category by itself, okay? So remember, there's another idea, which is that we can take the product of two categories. So we take the product of category C with itself, and we get C times C. So remember that C times C has objects which correspond to pairs of objects of C, and it has arrows which correspond to pairs of arrows from C, and we compose these arrows like this, okay? And also if we have an arrow F1, F2, let's say that goes from object A comma B to object A bar comma B bar, well then we better have that F1 goes from A to A bar, and F2 goes from B to B bar, okay? So that's a very short summary of how the product of categories works. Now don't get confused by the terminology here. There's two different sort of products in action here. One is the product of categories, and the other one is the categorical product, which is the product of objects within a category. And that's what we're trying to construct, but we're using product of categories to construct that, okay? So we have category C, we have the product of C with itself, and we have a functor, okay? Remember, in the definition of these terminal morphisms, we need a functor. And our functor is this sort of triangle thing here, and this is called the diagonal functor. Now the way that this works, it's a functor from C into C times C, and it takes an object Z and it sends it to the object Z comma Z, okay? So it just takes an object and then sends it to the pair, which is like two copies of that object in this C times C here. And what's it do to arrows? Pretty much the same thing, okay? It sends an arrow H in C into an arrow H comma H in C times C. Okay then, so all we're going to do now, say we want to take the product of a pair of objects in C, X and Y. Well, that means that X comma Y must be a object in C times C. And all we're going to do is we're going to define a terminal morphism from this functor, from this diagonal functor here, to this object X comma Y in C times C. And that's it. That definition, when we look at it, we look at how such a terminal morphism is defined, you know, we're going to get that it looks exactly like a product. It looks just like the categorical product of x and y. So let's have a look at that. So terminal morphism from this functor to xy, what is it? It's an object R in C. Now we're going to see that this R actually is the categorical product of x and y, so we could call it x times y, but I don't want to be preemptive, so I'll just call it R for now. So it's going to be an object R and also an arrow from delta R into x comma y. Now I am being a bit preemptive here, calling this arrow pi1 comma pi2, but that's just a name so far, okay? And it has to be such that for any z in C and for any arrow from delta of z into xy, there has to exist a unique h from z to r, which is going to be such that if we compose this arrow pi1 pi2 with delta h, we get this arrow f comma g, which went from delta z into x comma y. Okay, so all we're going to do is just think about what this definition means, and we'll see it's precisely the definition of the categorical product of x and y. So how can we see this? We'll just ask ourselves, what is the delta of stuff? So what's delta of z? Well, we know it's z comma z. And what's delta of r? That's going to be r comma r. And what's delta of h? H comma h. Okay, so all we've done is taken our definition of a terminal morphism and then applied the definition of a diagonal functor to express what these different deltas of things are, okay? And now I want to argue that this is the familiar definition of a categorical product of x and y, okay? So basically what I'm trying to say is that R is going to end up being the categorical product of x and y. But how are we going to see this? Well, let's just read this definition and see what it means in terms of this category C, okay? So we have objects x and y, and we have an arrow pi1 from r into x. And we have an arrow pi2 from r into y. And it's such that for any z which has an arrow f from z into x and g from z into y, there's going to exist a unique h such that pi1 after h equals f, and pi2 after h equals g. That's exactly the definition of the categorical product which we wanted, okay? Okay, so now we can see that the categorical product of two objects corresponds to a kind of universal morphism, okay? it's specified by one of these universal properties. It actually corresponds to a terminal morphism, okay? And later we're going to see that any two kind of similarly defined universal morphisms end up being isomorphic to each other. So remember before we proved that any two categorical products of a given pair of objects end up being isomorphic. Well, that was just a special case of what we're going to prove today works for all of these different kind of universal morphisms, and there's so many different kinds. Categorical product is just a sort of drop in the ocean of these different universal constructions that we can do. Okay, so we're going to have a look at another super important idea in category theory, and it's going to correspond to one of these universal morphisms, okay? So this is the idea of an exponential object. So what is it? Okay, so consider a couple of objects, A and B, in a category. Now, there may be some arrows from A to B. There may be lots of them. And, you know, we have this collection of arrows. Now, obviously that's represented as itself. It's a collection of arrows. But sometimes there's a curious kind of self-referential thing going on where there may be another object which actually also represents that collection of arrows. And if there is such an object, we usually call it b to the power of a. Now, what is this? Well, this is another object which somehow represents this collection of arrows from A to B. So what kind of categories have this sort of thing? Well, think about the category set, which has objects as sets and arrows as functions, okay? So in that, we'd say, well, there's a set of functions from A to B, and that's a set, so it corresponds to another object. So the category set has this curious property that there's somehow an object b to the power of a which represents this collection of functions going from A to B. And, you know, we talk about this in common language, okay? The set of functions from A to B, it's a set, so it should correspond to an object. But it's curious that this is an object in the category, and we can actually pick it out using a categorical construction, in particular one of these universal constructions. Now, this works in other categories as well. So in the category of categories, if so, this then A would be a category and B would be a category, and this would be the collection of functors from A to B. And in that case, this B to the A, this exponential object, I'm going to show you how to construct. If we did the construction in that case, we'd get the functor category, okay, this category of functors from A to B. So this is really a very powerful idea. So let's talk about it, okay? So let's just go through the definition for a start. So we have a category C, and we're supposing that the product, the categorical product of each pair of objects is defined, okay? We're going to need to use the idea of categorical products in order to do this type of construction, okay? So here comes the definition then. An exponential object is an object b to the power of a in our category, and an arrow e, which goes from b to the power of a times a, so this is categorical product, to b, okay? So it goes like that. And it's such that for any sort of imitator, for any object z, and any arrow G which goes from Z times A into B, there's going to exist a unique H. A H from Z to this thing B to the power of A, which is going to be such that it makes this diagram commute, okay? In the sense that E after H times IDA is G. Okay, so let's first understand what this means. So there's a few things going on here. One thing is this categorical product. So if you like, to begin with, you can just think of this as happening in the category set. Okay, so this would correspond to Cartesian product. The other thing going on is this. Okay, so what's this? Well, this is, if you recall, this is how a arrow gets lifted under a sort of functor defined by a categorical product, okay? But I mean, if you want to think of this in the category set, then simply we just have the, so okay, this would just be an arrow from Z times A to this. So if we have a general element W comma A, little a, in Z times A, and then we do this function on it, what are we going to get? Well, we're just going to operate H on the first element and IDA on the second element. So we'll just get H of W, and we'll leave this little a alone here. Okay, so that's how this would work in the category set, but you can refer to my previous video. I think it was called Duality and Functoriality or something like that, for a general definition of how this kind of a functor defined based on categorical products can convert arrows, because we can, you know, here's what it looks like in the category set, but this kind of conversion of an arrow into something that's involving categorical product can be done much more generally, okay? If you're working in the category set, or if you're into functional programming, say, there's a much easier way to understand what this picture's showing, and basically it's illustrating something called currying, okay? So if you kind of change your perspective a little bit and think about this Z times A, so what's G from Z times A into B? Well, it's going to be a function with two inputs, okay? An input W from this set Z and an input little a from this set A. And it's going to send those two inputs to a member of this set, capital B here. Okay, so what we're going to do now, let's say we have a value W of Z. So what we're going to do is we're going to make a function, H of W, which we'll call K subscript W. And this is going to be a function which sends a value of A to G of W comma A. Okay, so we're doing currying because we're making this function here, which is just a function of one input, but it's sort of defined in terms of this W, so it kind of memorizes how G works, and then it's ready to just do the same thing when it's given an A. Okay, so K of subscript W of A is going to just be G of W comma A. Okay, so that's what this unique intermediary arrow does. It changes a value of Z into a kind of function which does what G does using that value of Z, okay, but it leaves the other kind of A component variable, Okay, so that's still the input of this function here. And so we have a w comma a, and then when we do this arrow here, well, we leave the a alone, but this w becomes a k of w. So now we have a pair, k of w a. And that's all we get here. And then e is just a kind of evaluation function. Okay, so it takes this pair, this function that would operate on a and an input a, and it just operates k of w on a. So this is just currying, okay? And this is what the exponential object does in the category set. Now bear in mind that this is a much more general kind of concept, and it does apply to lots of other categories. So like I say, if A and B are objects in this category of categories, then b to the power of a, this exponential object, is going to correspond to the functor category. Okay, so this is a very kind of general idea, and it corresponds to a universal property. Okay, so this actually corresponds exactly to a terminal morphism from this functor here. This is a functor which just takes an input and then does the categorical product of it with a. So this corresponds to a terminal morphism from this functor to b. Okay, so if you just look at the definition of the terminal morphism and just compare it, I mean, the diagrams look almost exactly the same, and you can see that this is just exactly what it is. It's just another universal morphism. So we have that, you know, any two things that would satisfy this condition of being exponential objects are going to be isomorphic to each other. We have lots of nice results about this. Okay, so now we're going to understand what numbers are using category theory. So basically, we've done various constructions in this category set. Okay, we've figured out ways of picking out elements, understanding when sets are isomorphic, define the product of sets, and we've done this in terms of category theory, this kind of categorical view of set theory, which basically corresponds to looking at this category called set, this category that has objects as sets and arrows as functions from one set to another. And now we want to identify the set of natural numbers. This is the set of numbers 0, 1, 2, 3 and on, and it's pretty amazing that we can do this, and it's remarkably simple actually. I mean, a lot of mathematicians, and I used to be one of them, believe that the natural numbers is the sort of ultimate bedrock of mathematics. I mean, I think it was Kronecker who said God created the integers and all else is the work of man. But since I've been studying category theory, I've really changed my viewpoint on this. I think that you know, categories are much more fundamental than most other stuff in mathematics, and indeed we can define the natural numbers using this tiny little diagram. Okay, so just 5 dots and 6 arrows, and we have a definition of the natural numbers. I mean, this is really great in my opinion. I mean, natural numbers are so important in mathematics and so fundamental, and yes, on one hand they seem very kind of simple and elementary, but on the other hand, I mean, you know, they're infinite, they have lots of complexity, prime numbers, this kind of thing. So it's quite remarkable, I think, that we can do this. We can identify this set that represents the natural numbers just using simple ideas from category theory. And moreover, once we have this type of definition that I'm about to explain, we can apply it to lots of other categories as well and identify things that look like natural numbers in lots of other categories. Okay, so let's begin. We're assuming we have a category, and we're assuming that it has a terminal object. So recall that a terminal object is an object that has exactly one arrow into it from any object, okay? And we're denoting this terminal object as 1 here. And so what is a natural number object? What is this thing in category theory that represents the natural numbers? Well, it's actually 3 things. It's an object called n and 2 arrows. An arrow called s, which goes from n to n, and an arrow called z, which goes from the terminal object into n. Okay? And it has to satisfy certain properties. In particular, it has a kind of universal property that for any setup like this, where we have some object A with an arrow Q into it from the terminal object and an arrow F from A to itself, we want there to exist a unique U which is an arrow from N to A that makes this diagram commute. Okay, so it works in the sense that Q equals U after Z and F after U equals U after S. Now that's the definition of a natural number object. So okay, well, what does that mean? Okay, well, let's interpret this stuff in the category set. So remember, a terminal object in this category set is a singleton set. Okay, so just a set with one element. And also remember that remember the way that arrows out of the terminal object work in this category set. They essentially pick out an element of the target set for us. Okay, so there's just one element in this singleton set here, this terminal object, and so an arrow from this singleton set to another set is just going to point towards one element in the target set. So how do we interpret this Z here from the terminal object into N? Well, N here represents the collection of natural numbers. Okay, so this is what we're really trying to define. So this is, all the non-negative whole numbers, 0, 1, 2, 3, and so on. And Z here is essentially going to pick out the 0 here, Z for 0. So it's going to be a function that sends this single element here of our singleton set into 0. And okay, so that's what this means. This is the set of natural numbers. What about S? Well, S is the successor operation. Okay, so it sends every natural number to that natural number plus 1. It sends 0 to 1, 1 to 2, 2 to 3, and so on. Okay, so this is the sort of basic idea of winding on the numbers. Now, of course, in this context, if we just stopped our definition there, we wouldn't have any means to really say anything special about what this Z, N, and S mean. Okay, so the sort of meaning that these things obtain is, and the meaning we ascribe to them here is because of the way that they relate to these other kind of things in the category. Okay, so what's the rest of this definition saying? It's saying that if we have a set A, so this can be any set, and then we have a arrow Q from the terminal object into A, so that would be just picking out an element of this set. And if we have a function f from this set to itself, like this one here, this f, so then we have that there exists this unique arrow with certain properties. Okay, so essentially what we have is that there's a unique arrow u from n into a which satisfies these two equations here. Q is equal to u after z, so that's this diagram commuting, and u after s equals f after u. So what does this stuff mean? Well, let's let me rewrite this as Q equals u of 0. Okay, so we know that z here represents 0, and I'm just using a subscript instead of, you know, writing u after 0. How about this condition here? Well, we know that this condition, when we're interpreting it in the category of sets, we can basically say that this means that this function is equal to this function. Another way of saying that is that given any input, evaluating this function of the input gives this function of the input. So let's sort of simulate a generic input here. A generic input can be represented as a kind of arrow from the terminal object into n. So it might be going from a terminal object into 2 or into 3. So this I here represents a kind of number which we are picking from this set of natural numbers. So we can write this condition here as u after s after I equals f after u after I for all I from the terminal object into n. Okay, but let's interpret that more. What's s after I? Well, I represents an element of n, and we know that we want s to represent this kind of successor operation. So s after I, we can write that as I plus 1. Okay, so I can rewrite this condition as u of I plus 1 equals f of u of I. And now we start to see what this definition means. It's illustrating how we can label the different kind of states of a very simple dynamical system where we just start with an element here and then we keep applying this function f over and over again. So here I've got one copy of A and one copy of A in a function. Let me just redraw that. And I'll just redraw this function internally. So it sends A to B, and it sends B to A, and it sends C to A. So that's our function f. And now how is this working? Well, we can actually see now that the u that satisfies these conditions is uniquely defined, okay? So we know that we need q is equal to u of 0. So we know in this picture q is picking out element A, so this is q is u of 0. And we know that u of I plus 1 is f of u of I. So what's u of 1? Well, it's going to be f of A. So here's u of 1. And what's u of 2? Well, u of 1 plus 1 is f of u of 1. So u of 2 is f of u of 1. So that's going to be f of B, which is A. And then apply f again, we get u of 3. And apply A again, we get u of 4. So basically, all this definition boils down to is saying that the natural numbers have they're sort of defined by having the property that if we get any set and we pick a starting element q in that set, then we can say, okay, 0 gets sent to q, and 1 gets sent to f of q, and 2 gets sent to f of q, and 3 gets sent to f of q. So we're just saying that we can sort of label the different members of this sequence of things that we get by starting somewhere in a set and repeatedly applying a function from that set to itself. Okay, so I'm trying to convince you that this kind of natural number object really represents the set of natural numbers in this category set. Now, so far I haven't really done that, but what I'm trying to get across first is the idea that the natural numbers do indeed have this property, that they are a natural number object. Okay, so I think it's quite clear that we can make a function like this which satisfies these conditions, this one and this one. So given a set A and a kind of function to itself, we can, and a way to pick out a starting point Q, we can then kind of label the different, the sequence of things that we get, the kind of trajectory of Q as we keep applying F to it in this sort of dynamical system. Is it clear that this is the only arrow from the natural numbers which makes this and this hold? Well, it should be, okay, because we know there's only one way to pick u of 0. We have to send that to q, and then this forces us to pick a particular value of u of 1 for f of q, and then u of 2 is f of q, and so clearly everything is forced into, you know, we're forced to pick one u. There's only one function u from n to a that makes this work. So we do indeed have the uniqueness here. So that means that the set of natural numbers in the category set is a natural number object, okay? But we're not really done because how do we know that there aren't going to be other sorts of things satisfying this definition here which are nothing like the natural numbers? Okay, well, the reason we know that is because this type of definition is actually a universal property, and basically it turns out that any two things which we could call natural number objects, according to this definition, are going to be isomorphic to each other. Okay, so if we have anything satisfying this condition in this category set, it's going to be isomorphic to the set of natural numbers. And that's quite a remarkable result. So this really picks out for us the essence of the kind of counting numbers. The basic essence of them is that we can keep track of these, we can label the different, the sort of sequence of goings on when we keep applying a function f repeatedly, starting with an element q in an arbitrary set A. Okay then, so this idea of universal morphisms and universal properties is super important in category theory. Some people say it's the most important idea. And so we want to get a good kind of understanding of what this property means. And in particular, there's a way we can get a really kind of succinct definition of what a universal morphism is. Now, I have already given you a definition, but it's kind of long-winded, you know. It's like, oh, well, if we have such and such, then there exists this, such that. And there's a really short definition of what a universal morphism is. But in order to understand that, we have to look at another idea called the idea of a comma category. So I'm going to define this. Now, this is a little bit abstract, okay? So it might be a bit hard to understand if it's the first time you've seen comma categories. This is not going to be a kind of linchpin of this series of videos. So don't worry if this is hard to understand. But I do want to tell you about it because it's going to give us a much better understanding of what a universal property is, and also we're going to get an important result out of this, which is that any two universal morphisms between the same things are going to be isomorphic. Okay, so we already saw this kind of phenomenon occurring when we showed that any two categorical products of a given pair of objects are going to be isomorphic. But this idea goes much deeper, and we're going to really see where it comes from once we understand what comma categories are. Okay, so what is a comma category? Well, it's a special kind of category, and it's made out of objects and arrows from three different categories. So we've got three general categories, U, C, and L. And we've also got some functors between them, okay? So we've got general functors, a functor U from U to C, and a functor L from L to C. Okay, so what is the comma category? Well, it's written as the functor U with a downwards arrow and then the functor L. Okay, so what are the objects in this comma category? Well, the objects consist of triples. An object A of U from category U, an object A of L from category L, and a arrow. And this is going to be an arrow from category C. And what about this arrow? Well, it just has to be an arrow which goes from U of A of U to L of A of L. Okay, so we have this kind of picture, or at least this picture's a bit too big for what we're talking about, but you can see what I'm on about here. Okay, so here's an object of U, A of U, and here's an object of L, A of L. And then an object in this comma category consists of A of U, A of L, and alpha, where alpha goes from the image of A of U under this functor U to the image of A of L under this functor L. Okay, So it's a special kind, so the objects of the comma category are triples, an object from U and an object from L, with this special kind of arrow here of C, which connects where these objects get sent to in C under these different functors. Okay, so we have all such triples constitute the objects in this comma category. Okay, so what about the arrows in the comma category then? Well, we can have arrows like this. Okay, so an arrow we'll call F, which somehow goes from this triple, A of U alpha A of L, to this triple, B of U beta B of L. So what's an arrow like this actually consist of? Well, it's going to be a pair F of U comma F of L, where F of U is going to be an arrow of category U, going from this object to this object, so going from A of U to B of U. And F of L is going to be an arrow in this category L, which is going to go from A of L to B of L. But we also require, in order for this to be considered an arrow, okay, so we require that this kind of square here has to commute. So we require that beta after U of F of U is going to be equal to L of F of L after alpha. Okay, so these arrows here are sort of pairs of arrows that make these kind of squares commute. Okay, so now we know what the objects are of the comma category, and we know what the arrows are. And so here's a kind of picture where we can see what a sort of arrow F from one of these triples to another of these triples, an arrow of the comma category, we can see what it looks like in this category C up here. So we have this arrow F of U from A of U to B of U, and we have this arrow F of L from A of L to B of L. And if this is to be considered an arrow from this triple to this triple in the comma category, it has to make this kind of square here commute. Okay, so going along here and then here gives us the same thing as going along here and then here. Okay, so now we know what the objects are and the arrows. We need to know how to compose the arrows, and that's quite straightforward. Okay, so these arrows in the comma category are pairs, and if we want to compose them, say we want to compose an arrow G of U comma G of L with F of U comma F of L, well, all we do is just compose the components. Okay, so the result is going to be G of U after F of U comma G of L after F of L. So we've seen this kind of mechanism of setting up arrow composition before when we were talking about the product of categories. Okay, so it's a similar kind of idea here. But how do we know that this is actually going to give us another arrow of our comma category? Well, we can see that well, I mean, effectively, we can see that by kind of extending this sort of square here. We'll have another square that represents what's going on with G. And then we know that this square commutes and this square will commute. And then we can prove that the big square commutes as well. So this is going to give us another arrow of our comma category. Okay, the composition of this arrow F with another arrow G. Okay. And finally, we need to know what the identity arrows are. So what's going to be the identity arrow associated with an object like this in a comma category? Well, that's just going to be the pair ID A of U, comma ID A of L. And I'll leave it up to you to check that that does actually work like an identity arrow for this kind of object here. So that's it. We know what the objects are. We know what the arrows are. We know how to compose them. We need to show composition is associative, but you can kind of see that by the way this arrow composition is defined in a kind of pairwise fashion, that, you know, the arrow composition is going to be associative in U and it's going to be associative in L. So if it works in both sides of the pair, then it'll work in this setup here. And we have these identity arrows. So yes, this is a category, a comma category. So we're now going to sort of look at a specialized case of this where we can define what a universal morphism is. Okay then, so what we're going to do is we're going to use this idea of a comma category to give a simple definition of a terminal morphism. Okay, so we're going to arrive at a definition of a terminal morphism from U to X. And what I want to convince you of is I'm going to make a special kind of comma category, and I want to convince you that this terminal morphism is going to be a terminal object of this comma category. That's simply, you know, it's a definition, an equivalent definition of a terminal morphism, okay? So we're basically going to get a view of terminal morphisms as terminal objects in a special category. So we start with the general definition of a comma category, and then we're going to restrict it by picking L here, this category on the right, to be a very special category, and that's just going to be the category which just has one object that we call 0 and just one arrow, the identity arrow. And now what's this functor L which sends this little thing into C? Well, it's just going to send 0 here into this object X of C that we're interested in. And it's going to send the identity arrow of this thing to the identity arrow of X. So this type of comma category is often denoted as U downwards arrow X, where X is really an object of C, but sometimes people write X to denote this kind of X-valued functor. We're calling it L because I like to separate out things which are different kinds of beasts. So anyway, let's just now ask ourselves simply, what are the objects and arrows of this comma category, A downwards arrow L? Well, the objects are going to be triples. So it's going to be an object A of U, and the only object 0 of L, and an arrow alpha, which is going to go from U of A of U to L of 0. We know L of 0 is just X, okay? What about the arrows then? So we know what the objects are of this comma category. What about the arrows? Well, we'll have an arrow from A of U alpha 0 to B of U beta 0. Let's say we have an arrow F. Well, what do we know about that F? Well, there has to be a pair, right? Remember the definition of the arrows in the comma category, they're pairs. An arrow from here to here in U, and an arrow from here to here in L. Well, an arrow from A of U to B of U, we can just write that as F of U. And there's only one arrow from 0 to 0 in L, and that's the identity arrow of 0. Okay, so the arrows in this are pairs, f of u, id 0, and they have to be such that this diagram commutes. This is a definition of the arrows in a comma category. So we have that beta after u of f of u equals L of id 0 after alpha. But we can simplify this, okay, because we know things. We know that L of 0 is just going to be x. L of 0 is x. We know that L of id 0 is idx. So we require that this square commutes. Okay, but why are we bothering to put an ID here? Identity arrows don't do anything with composition, so we might as well just collapse these two bottom parts of the square together. I mean, so all we really require for an arrow, I mean, the content is just we have an f of u, which makes a diagram like this commute, okay? So we can forget about these zeros that we're carrying along for the ride. Really, our objects are just an object of u and an arrow from u of a of u into x. And they have to be such that when we have two of them, the arrows between them are an arrow from a of u to b of u, f of u, which if we lift it under u, it makes this diagram commute. Is this starting to look like the definition of a terminal morphism to you? So now we understand what the arrows are in this comma category, let's ask a very profitable question, which is, what is a terminal object in this comma category? And so we see a terminal object is going to be a triple b of u beta 0, such that for every triple a of u alpha 0, there's going to exist a unique f of u comma id 0, which is going to be such that this kind of diagram has to commute. Okay, so how can we interpret this? Well, what we're basically saying is that, I mean, we can forget about these zeros and the ID 0 here. They're kind of meaningless, okay? What's important is that the terminal object has this, it's going to be an object of u, b of u, and it's going to be an arrow beta from u of b of u into x, and it's going to be such that for every a of u that's image under u has an arrow alpha into x, we're going to have that there's going to be a unique f of u over here from a of u to b of u that's image u of f of u makes this triangle commute, okay? And that is exactly the definition of a terminal morphism from u to x. Okay, so we see that the terminal objects of this comma category here are precisely the terminal morphisms from u to x. Okay, so now we have an equivalent way to define a terminal morphism from u to x. And also, what do we get out of this? Well, we get a very, very simple short proof that any two terminal morphisms from u to x are going to be isomorphic. Why? Because terminal objects are isomorphic, okay? If we have two terminal objects of the same category, they're going to be isomorphic. I proved that in either my first or second video in this series. And, you know, so we already know now that any of these terminal objects are going to be any of these terminal morphisms are going to be isomorphic to each other. Okay? That deals with half of these kind of universal morphisms. You might be wondering, well, okay, what about initial morphisms? Okay, so we've already seen now that a terminal morphism from u to x can be considered to be a terminal object of u downwards arrow x. What's the deal with initial morphisms then? Well, the initial morphisms just have a very similar kind of existence. They are just corresponding to the initial objects of the comma category x downwards arrow u. Okay, so if you just repeat the construction that we've just done, except this time you have your sort of x valued functor working on the left hand side rather than on the right hand side, and then you say, well, what are the initial objects of that category? They turn out to be equivalent to the initial morphisms. And so now we know that any universal object either corresponds to a terminal object of a comma category or an initial object of a comma category. And also we know that any two initial objects of a category are going to be isomorphic. So again, we know that any two initial morphisms involving the same things are going to be isomorphic to each other. So there we have it. Like, we know now that universal morphisms have this great property that if we have two of them specified in the same way, maybe they correspond to different stuff, but they're going to be isomorphic to each other. Okay, so that's a very useful concept. We've already been really using this notion when we talked about how categorical products of the same pair of objects are isomorphic to each other. But now we understand why in a much more general kind of, from a much more general kind of viewpoint. Okay, so there's actually some more content to this video which I made on universal morphisms. I also made a proof that natural number objects can be considered to be a universal morphism. Now, this video seems like it was getting too long, so I decided not to include that proof in the video, and I've actually decided not to put it on my main kind of YouTube channel because it doesn't really fit in with this kind of idea of this course being as kind of simple and concise as I can make it. But I have put that YouTube video online as a unlisted YouTube video, and if you look in the description below this video you can see a link to it.